This talk, in this seminar, I'm going to talk about geometric engineering from string theory and its relation with quivers and, in particular, quiver gauge theories. So the starting point would be the study of these three branes. The motivation is the study of these three branes at threefold singularities. And we have, in particular, the word volume theory that we get from probing these three branes on the singularities are four-dimensional supersymmetric theory that are described by quivers. That can be described by quiver. And in latest years, there have been developed several techniques, mathematical techniques, to extract a quiver with superpotential directly from the singularity. So the motivation for this talk will be to study explicitly two examples, which are these two that I draw here. The first is a prototypical example that is it is more studied, and there is more literature on this, and it is the conifold, which produce an abelian gauge theory. And the second example is slightly more complicated, is the Laufer example, which produce a gauge theory, which gauge theory would be a non-abelian one. Okay. So the general goal is to show explicit the flop transition of these between the two phases in these threefold singularities. And we are going to talk about, we're going to develop the seminar in these 4 points. First of all, we start from matrix factorization with some hints on matrix factorization and how to extract quivers from that. And so how to associate to a threefold singularity a quiver with and study its path algebra. Then I'm going to recall some definitions on quiver representations and some conditions that allows us to study its stability. And then I focus on the quiver gauge theory that we can build out of these quivers. Finally, I'm going to reproduce all the calculations and in these two examples. And the goal is to explicit parametrize the exceptional P1 that we will find by resolving these singularities. So matrix factorization is a procedure that starts from an hypersurface in C4, given by the zero locus of a polynomial, and we can associate to this hypersurface two matrices that satisfy the relation here depicted in highlighted in red. So they commute, and their product is proportional to the identity. And the proportion factor is precisely the polynomial that defines the hypersurface. Then we want to study R module, this particular R module that are the co-kernel of psi, which can be seen to have a free resolution, an infinity free resolution, which is asymptotically periodic of order 2, meaning that we can create an infinite exact sequence with these two maps, C and phi. In order to have a smooth resolution, we need to produce a non-commutative enhancement of this ring, and in particular, we would the procedure described by matrix factorization is to basically exchange the coordinate ring R with the C algebra and also the complex algebra and also R module A given by all the endomorphisms of the following R module in the parentheses. Here we will focus only on matrix. In this parenthesis, every module comes from a possible matrix factorization, but in these two examples, we will study the procedure when A is given only by one R module of type cokernel of psi. What? The difference between A and the mice?
And i's. So, I mean, different matrix factorization.
Yes. Well, matrix factorization of a given hypersurface is not unique. Yes, exactly. And we can, here it is a bit technical, why we have to introduce this non-commutative enhancement, but basically is because is related to the fact that we want a smooth resolution. So in these two cases, we just need one modules, but there are some other kind of hypersurface in which to have to have these smooth resolutions, we will need to add more and more R modules of type MIs. Okay, I recall some facts about quivers. First of all, we have a path algebra, which in here I indicated Q0, the vertices, and Q1, the edges, and H and T are head and tails of each edge. The product of the path algebra is a concatenation, and here it is the path algebra generated by all possible paths with the formal sum. The key fact is that we need also to introduce to study quivers with the relations. So basically, we introduce some set of relations which are finite linear combinations of paths. And adding this relation means to quotient out over the bilateral ideal of all these relations. And the goal will be to find a realization of A, so defined as above, so as the endomorphisms of R plus M, to realize this C algebra as a quiver path algebra. So, as I said, I focused only on the case when we have only one matrix factorization, or when we need only one matrix factorization. And so the path algebra clearly decomposes in that way. And the procedure to build the quiver is, first of all, associate to each module are included a vertex, for example, here, a vertex, and to each vertex a module, okay. And then to study the possible generators of the sum of the homomorphisms between these two vertices. And then we have to find the abstract relation, and I will tell some constraints that allows us to find these relations. And if necessary, we have to add odd loops between the nodes. Yes, loops on the nodes to complete the algebra. In the case, it's not fully generated by these words. So, for example, in this case, we can choose as generators of the homomorphisms between R and M the column vectors of the free module RD. So here, for example, the alphas. And for the generators for the other morphisms, from M to R, we can choose precisely the rows of the other matrix phi. Because, in fact, they satisfy, yes, because given the fact that b times psi is equal to 0, because of the relation between the two matrices in the matrix factorization, these rows can generate all the cokernel of psi. Some constraints that can be implemented. Well, first of all, the morphisms of R should commute because it has just one generator. And then, in general, we can have some relations between the entries of phi that we can implement. An assumption that here, in these two cases, is satisfied is that the coefficients of the matrix psi can be expressed by linear combination of the coefficients of the matrix phi. And in these cases, we have other two constraints that would be the one that we will use. One coming just from the fact that psi times phi is equal to 0, and the other from the fact that some morphisms are just the zero morphisms because we are essentially because they are in the image of psi, and we are searching for the cokernel. Another tool I should introduce is the quiver superpotential, and in particular the cyclic derivative. So cyclic derivatives are defined in that way. So basically, we start from a cyclic path, and we erase every. Maybe I can do an example. Yes, the example I reported there is more clear, because if we have some cyclic path, the cyclic derivative, for example, of I can write it. Just to see how they work. A1, okay. 3, 2, 4. In this case, we erase A3 and we start from A1 and complete the cycle. So A1, A7. Here we have two factors A3, so it would be A2, A3, A4, and here minus A4, A3, A2, just to see how they work. So a quiver we say that a quiver admits superpotential, a quiver with relations admits superpotential if the relations can be expressed as a cyclic derivative of a superpotential W, which is just a linear combination of the cyclic path. And of course, not all quivers and with relations admit a superpotential. Here I just stated an example that the quiver with, for example, the quiver with one node and n loops, so A1, A2, AN, with the relations that they commute, that every loop commute, admit a superpotential if and only if n is equal to 3. Okay. Then I also recall the definition of quiver representation. For example, we have a finite representation in which to each vertex we associate this time a vector space, a complex vector space in this case, and to each edge a linear map. And the relations would be just a linear combination that produce the zero map, the zero linear map. The dimension vector is defined as follows. And we can study also morphisms of relations defined, morphisms of representation is given by the condition that essentially that condition there, so that we have some linear maps between the vector spaces to each edge, and they produce a commutative diagram with the linear maps FAs of each edges. And a result in quiver representation that I reported here is that given a quiver with relation and A its path algebra, we have an equivalence between the category of representation of quivers and the modules over its path algebra A. Okay, here again this would be I introduced this factor to arrive to some stability condition that will be used later. We have a symmetry group that is the general linear group, the products of all general linear group of each dimension that acts by conjugation. And we have one parameter subgroup with trivial action, which is this delta. We will say that two representations are isomorphic if and only if they are in the same orbit under the group given by the quotient of the general linear group and delta. And in general, to study representation of quivers with relations up to isomorphisms can be very difficult. And we can introduce we can define the character as follows to add extra information. And here a technical requirement to use a technical requirement to use properly quiver GIT is that the character acting on delta would produce only the set with only the element 1. And this will translate in saying that that particular condition, so that theta, the vector theta, that we can fix times d times the dimension vector is equal to 0. Okay.
Why is this technical requirement is something similar to condition? What's the meaning?
Specifically, I don't know. I read that it is required to use some construction in Mumford theory of GIT. So I think it's an algebraic constraint, but I'm not. Yeah, to ensure stability, to study the stability, once fixed a theta, a vector theta, we should require one of the conditions we ask is that theta times d is equal to 0, and this comes from this other condition. I think that stability can be studied both from from the point of view of theta and the character. So sorry, can you repeat? Yeah, no, then I can, for example, here I have the condition of stability more precisely. Okay.
Yes. So you have several terms, some of them will positive and some of them negative. Each vector multiple. And some of them are positive, then negative. From that condition, it is a bit unclear.
I mean, so for example, okay, I should to study the stability. Well, we have to say what is a subrepresentation, which is just a choice of subspaces for each node and a restriction of the linear maps to these subspaces. And fixed theta, we can say that the representation is semi-stable if theta times the dimension vector of each subrepresentation is greater or equal than 0. But here we have already imposed that theta times d is equal to 0 for the dimension vector of the general representation in the first line. And an equivalent condition that we will use in this formulation is that the path from in the nodes generate all the morphisms between the negative and the positive node, where negative is intended that since theta times d is equal to 0, some of the entries would be negative and some of them positive. And an equivalent, we can say that an equivalent condition is requiring that all the paths the path in the quiver generates all morphisms between negative and positive. And okay, this can also be rewritten through these D-time conditions, and which are stated. Yeah, here. In the conifold, I will have in the conifold I will have a C here and a C here as vector spaces, because the rank of both our modules is 1, and the two gauge groups are so U1 and U1. Whereas in the Laufer's example here, I will have C and C2 in this case. U1 and U2. And this would be the gauge group of the quiver gauge theory that will arise at the end.
What about the condition theta of d equal to 0? In this example, and write the condition for that.
Yeah. Well, in this example, it's just that example theta. Okay, we have theta plus theta m equal to 0, so we can parametrize theta as one psi c. And here we will have theta plus 2 theta m equals 0, and so theta would be parameterized by minus 2 psi, for example, in these two cases.
And so the bigger conditions.
I will then I will explain both the conifold and the Laufer example. I just go on with the. Okay. No. See. Okay. Okay. Other condition that we can. Okay. So we have also these D-time conditions written in the as follows. and where in here the phi are the maps associated to each edges that I will further rewrite for these two cases. I mean, they're written. Okay. So we obtain, we can derive a quiver gauge theory, or specifically the matter sector of a four-dimensional n=1 quiver supersymmetric gauge theory. The gauge group, as I said, is just the product of all unitary group for each dimension. And the field content is that to each edge we associate a field in the bifundamental. For example, if the edge goes from I to j, we associate a field in the bifundamental of UDI times UDJ. Okay, then we have the superpotential is precisely the superpotential of the quiver, written in with these fields, and the terms of the theory are precisely the stability conditions written above. Okay, let's go. And finally, we will study, for these two cases, also the exceptional curve, because we have that the moduli space of representation a dimensional vector with a fixed dimension vector correspond to a resolution of this singularity. And so we have this, we can have a blow-down map, a projection, and that associate to each quiver variables the coordinates in C4 in which the threefold singularity lives, and they should be invariant under the action of the symmetry group. We are interested in studying the fiber over the origin, so over the isolated singularity, and I will show how we can parametrize explicitly in this case the exceptional curve that arise from this blow-up, which is in both cases a P1. Okay. Okay. For example, for the conifold, we have the following matrix factorization with 2 by 2 matrices, and we say that we can see that their determinant is precisely 0. I mean, the determinant is the polynomial that describes the threefold, which is 0 in the coordinate ring, and they satisfy the relation of the matrix factorization. Here, these modules have both rank 1, and following the prescription given above to find the generators between the morphism through R to M and to M to R, we obtain the following two. For example, we can choose the following maps: alpha 1, alpha 2, beta 1, and beta 2. And beta 1 and beta 2 are just the rows of phi. And since the assumption given, since the assumption studied from to give the constraints is satisfied, we have the following two constraints on the maps. So they represent the quiver relations that emit a superpotential, which is called the Klebanov-Witten superpotential. Okay. Here, as I said, we have a dimension vector which is 1, 1, and the fields are just so complex scalars that transforms into a bifundamental of U1 times U1. And we can see that the diagonal U1 acts trivially on them. The stability condition is written, allows us to parametrize theta with parameter psi. And okay, and rewriting the d-term condition in this case will produce the following equation. Alpha 1 here is just the modules since they are numbers. So the following equation. And here we have already implemented the stability condition theta times d. Okay. Okay, for example, here we can fix one of the two phases, theta plus and theta minus, because we will study, sorry, I didn't say that, we will study the two phases, theta plus and theta minus, in that way. And we will follow the flop transition between psi greater than 0 and psi less than 0. So fixed one of the two phases, we have a resolution of the conifold singularities and a way to express the conifold, the C4 coordinates through the quiver variables, which, for example, is the one written there. And these four paths should generate all gauge invariant functions. And okay, yes, sorry. Then if we want to study the fiber over the origin, we have to impose the constraints of theta stability. For example, for theta plus, we obtain that we cannot have that alpha 1 and alpha 2 vanish simultaneously because we require that they generate the homomorphism between the two vector spaces, so they cannot vanish simultaneously. But and so, if we want to annihilate all the functions depicted here, we have to impose that beta 1 and beta 2 are both 0, and vice versa in the other phase, theta minus. Okay. We can beta 1 and beta 2 are the other two. I'm trying to no, because I'm studying the fiber over the origin through the resolution. Okay. Yes. Sorry. So so I want to study where these coordinates vanishes, and so since from stability condition I cannot have that alpha 1 and alpha 2 vanish simultaneously, I will have the beta 1 and beta 2 would be both 0, and vice versa for the other phases. Yeah, here I'm finding the exceptional curve through this resolution. Okay. We can summarize that with the two irrelevant ideals I plus and I minus, and the condition that their elements cannot vanish simultaneously. And imposing now the different conditions in the two phases over the origin, we will have the two spheres, alpha 1 plus alpha 2 squared equals psi, and for theta minus, the other one. And okay, in both cases, we have the a residual action of the diagonal U1 that allows us to send to see that the origin is essentially replaced by an S2 sphere. And here alpha 1 and alpha 2 parametrize so P1. And here alpha 1 and alpha 2 and beta 1 and beta 2 parameterize precisely the exceptional curve, are precisely the homogeneous coordinates of the exceptional P1. And this case is okay, and so we can follow the flop transition by studying. We can explicitly we have explicitly followed the flop transition by studying from starting from psi greater than 0, and then see what happens when there's a typo, psi when we pass to psi less than 0. A more complicated example and more interesting is the Laufer example. In this case, we have which is given by the following, by this equation, by this polynomial, and an example of matrix factorization is the one reported there. And in this case, I will not study all the way to find the quiver through matrix factorization, but essentially we end up with this kind of quiver reported here. So we have a map from R to M, and another one from M to R, and then two loops on the node given by the cokernel of the psi. And okay, and we have the quiver relations. In this case, are the one described there, and they still admit a superpotential WL. For example, a choice of the maps that satisfies these relations are the one reported there, where, okay, here it is a possible choice, and well, we can see that C, for example, is a row of the phi matrix of the matrix factorization. And okay. Here we have the dimension vector is 1 and 2, because M is this time of rank 2. And so we will have that the two phases that we want to study are -2. We will write that here. The two phases are theta plus is equal to -2, 1, and theta minus is equal to 2, -1. Okay. And the gauge group is U1 times U2. So in this case, the field content, describing the field content of the n equal 1 gauge theory would be associated to A and B, two fields in the adjoint representation of U2. In phi C, a fundamental of U1 times U2, and in D, a fundamental of U2 times U1. So essentially, we can represent these fields. A and B are 2 by 2 matrices, while C is a row vector and D is a column vector. Okay.
On these last two equations, you can explain why you need theta r plus 2 theta is equal to 0.
From the last one.
The last two equations.
Yeah. Okay. Okay, yes. If I trace the... Okay, I missed that. Okay, so yeah, taking the trace of the first row, we can... taking the trace of the second row. Yes, the first one is just numbers, while the second is matrices. And we obtain the condition, the stability condition, theta r plus 2 twice theta m is equal to 0. Okay. So now we can study the stability conditions. For example, for theta plus, we have that through some results, we can have that D, A times D, and B times D cannot be all collinear as to the two-dimensional column vectors. And we impose that they should generate all morphisms between R and M. While for theta minus, we have that to generate all morphisms, we need C, CA, and CB. And this situation can be summarized by given the two irrelevant ideals I plus and I minus, that once again will parameterize the exceptional locus over the origin, so the P1. Okay. And here again, we have a resolution of the singularity. We can study the resolution of the singularity. And for example, the coordinates are given by the following functions of the quiver variables. Okay. Okay. Here we want to study the fiber over the origin. We should have in mind that this gauge invariance in the field theory corresponds to traces of loops in the quiver. And at the end, the goal is to study the nilpotent to find the conditions such that the loops are nilpotent as the linear maps in the quiver representations. So, for example, if we study the loops on R, we have these two kinds of loops where here for AN and BM, I mean all the possible combination, for example, going all possible powers and products of A and B. So I can go twice around A, then B, or any way I want. And since they are just number, imposing the fact that they are nilpotent, we get that, okay, they are 0. While for the loops around them is slightly more complicated, because, for example, we have, well, the loops, we can go through C and then D, or then follow some paths in A and B, or then just going around A and B. And from the previous result of loops around R, we have around R, we have that this is automatically 0, and also the second kind of loops. And from the other, we obtain that the only non-zero loops remaining are A, B, and AB. Okay. So putting all together, we have that the fiber can be described by this ideal. Okay. And if we specify in the two phases, the fact that D, AD, and BD cannot be collinear ensures us that C is equal to 0. And so the ideal simplifies to this one, I reported here. And similarly, for theta minus, we have this other ideal, IP1 minus. Another factor that will be used is that A and B are proportional, essentially, because of all the relations we were given before. And now the goal is to find a basis, a convenient basis to see the P1 more explicitly. For example, using the gauge group, the symmetry group of the quiver representation, we can fix a basis in which AD and BD are proportional to the column vector 1, 0. Maybe I write it here. Okay. See, okay. So AD and BD are proportional to 1, 0. And D is just the column vector 0, 1. And as we said here, C is equal to 0. So we have general solutions to the D terms condition and F terms, so the relations, the quiver relations, which is the following. So I'll just write here 0, 0, 0. Okay. There's still we have used the symmetry group, but we have still a residual C star that we can use to that acts in the following way on the matrices A and B, and leaves D unchanged invariant. So we can see how, in these cases, since after this parametrization, alpha beta will just go to lambda alpha and lambda beta, we have that they can represent the homogeneous coordinate of the P1. And similarly, analogously, we can find the two solutions for theta minus. Okay. Here the determined conditions are rewritten in this way, and we have, okay, so having parameterized theta through the parameter xi, okay, and the idea is to find a way to follow the flop transition between the two phases, so between xi greater than 0 and xi less than 0. So we have the an ansatz that interpolates between the results in theta plus and in theta minus. And we can plug these ansatz into the D-term constraints and find the following result. So basically, here we have that, so we have that, I didn't say, okay, delta and gamma are just parameter for C and D. And in these cases, we have that in the theta plus phase, we have that gamma is just equal to 0. And so the condition is that alpha squared plus the modulus of alpha squared plus the modulus of b squared is equal to xi, while in the other one, the other condition is just equal to minus xi, with xi negative. And here we can still see how these coordinates are already implemented in the description of using the irrelevant ideals I plus and I minus. So we found a way to parameterize explicitly the exceptional locus P1. Okay. So in conclusion, in this talk, I I recalled the procedure of matrix factorization for singular threefolds and how they are how we can find non-commutative resolutions and study the post-algebra of the quiver they produce. I described how this quiver can give rise to the unequal one gauge theory given by a DC brane that probes the singularity threefold, and we find the two we studied two cases in which the in which we explicitly found the flop transition between the two phases for the exceptional locus P1. Okay, and I finished. Many thanks. And here is some bibliography. Are there
questions, comments?
if there is an equal one, there could be.
There is a truth that probably that this non-randomization theorem is not working. In principle, it can have some quantum fractions to their module spaces.
Honestly, I don't know how in this case, how. No, honest.
In the description only for the classical quantum of theory, or
No, well, we have now we have reproduced the if it is the description of the model of the quantum field theory or the classical field theory. I think no, we've given um, no, I think of the quantum field theory of the I mean we've described the quantum field theory of a D3 brain probing a threefold singularities. A threefold, or no, I guess. Yes. Oh, okay. So, but okay. No. So, okay. So yeah, I work up the classical superpotential. I thought. Okay. No. Then it's the classical. I thought that this result would be more powerful, but no. In this talk, yeah, I work out only the classical modular space. Let's say. Yeah. The Well, the superpotential of the quiver give explicitly the superpotential of the gauge theory. So in this case, we have, for example, the superpotential in red, and that would translate in the superpotential of the matter sector of the n=1 gauge theory. If there is no superpotential, I don't know to proceed in. Yes, yes, I think. Mm, if we cannot find those, no, yeah, I mean, I don't know if how to proceed if we don't find if we cannot rewritten the relation in superpotential. Um, in general, in these two cases, no, no, no. Or adding extra. If adding.
also put the symmetry on the bottom to still there is symmetry. So
There are other ways of comparing symmetry, like dynamic. I don't know.
but it doesn't describe completely, like get one symmetric theory and quantum level of what happens.
You have a symmetric graph as no particular field. There are also for symmetry preserving Laufer, but they can be worked on.
Okay.
Other questions? So if not, we can